Hello everyone, welcome back to the series of lectures on actinide chemistry. And as we have discussed a bit about the aquatic chemistry of F-block elements, so today we will try to learn something about pHpE diagram. And before going to the presentation, I just want to have a mention of the references that I have used for this presentation. The first is the chemistry of actinide and transactinide elements, and second is the aquatic chemistry. I've also used some of the program for the speciation plot that I have taken from the KTS, that is known as the Medusa or Hydra. Some of the images are taken from the internet or web as per the convenience. I have modified them. So these are the few references that I have mainly used. Besides that, whatever references I have used, I have tried to quote them on the respective slides. Before going to the next lecture, I would just like to have a mention of whatever we have done in the previous lecture, kind of recap for that. So there we have started with the electronic configuration, and we have seen that the group oxidation state of lanthanides are +3, whereas when you talk about the actinides, they can have a variable oxidation state starting from +2 to almost 7. So there we have seen that this kind of variation in the oxidation state of the actinides are mainly coming because here the filling happens in the 5s orbital, which is having close proximity with the 6d and 7s orbital, and because of that we are getting such a huge variation in the oxidation state. We have also learned about the different ions that are possible in the actinide, and we have seen that the divalent, trivalent, tetravalent, these ions are basically spherical. But when we talk about the other valency, that is pentavalent ion and the hexavalent ion, they are no more spherical but are linear. If you have to draw, it is like, suppose you have to take uranium, it is like uranium. This is called trans-dioxo compounds. So here we can see that the charges are 2+. So you can see the total charge is 2+, whereas we say it is like hexavalent, so uranium 6. But if you start about the properties of these ions, what you found that they are neither behaving like pure 2+ or 6+, but in between, somewhere in between. So lots of group has worked on this, and finally they have come to the conclusion that the bonding or the chemical properties of this kind of element, this kind of oxidation state, that is actinide we say in general, are dependent on the charge, which is 2.2 units in the case of pentavalent and 3.3 units in the case of hexavalent. We have also tried to see that what is the hydration structure of different actinides in the water, and here we have just discussed that for the trivalent they start with around 9 water molecule and they reach up to 8 water molecule, and there is a transition where we are having number of water molecule, some of them are having 8 and some of them are having 9. So there is a transition. This is about the first sphere, and we have also seen in the second sphere or the total hydration number is increasing in the reverse order, and we have tried to rationalize this by size and total surface charge density. So with this basic background, I would like to go to the next slide that now we are going to discuss. Yeah, so what are the different ionic radii? We have discussed about the lanthanide actinide contraction, and here just I have given you some of the values that are there in the different oxidation state for the ionic radii that start from trivalent, tetravalent, pentavalent, and hexavalent. This we have already discussed in the lanthanide actinide contraction. We have shown you some graph for that, so I am not going into much of the detail of this. This is just for your reference that some of the values are given, and as you can see, they are having a decreasing trend because of the lanthanide contractions or actinide contraction in the respective actinides. So once you are having a water, you add water into the medium, what will happen that your water will be there in the primary coordination sphere. So now the question arises that what is the coordination number of a given oxidation state? So here in general, the trivalent prefers +9, tetravalent prefers between 6 to 12, but generally 10 you can say, and the pentavalent, as I've shown you, that these are not the spherical ion but are the linear ion. So they have very different coordination number from 6 to 8. Hexavalent is again 6 to 8, and heptavalent, which is specifically exists in the alkaline medium, only having a coordination number of around 6. But this is a very rough estimate. So I can give you some of the example where the ions which are in the trivalent state can have coordination number which are very different from whatever I have written. So for example, in general, I have shown you this. This is the coordination number 9. This is the aqua molecule. You can see 9 water molecules are surrounded the lanthanum ion. But there are cases in which the coordination number goes as low as to 3. Why? Because in general, the coordination number depends on two factors. One is the size of your lanthanide ion, and the second is the ligand crowding. Or when I say ligand crowding, there are two very important factors, that is called first order crowding and the second order crowding. What I mean by this first order crowding or second order crowding is that, let us talk about the first order crowding. So when your ligands are very small molecule like this, a water molecule or having a nitrate ions, when your ligands are having a small molecule and they are directly coordinating like this, you can say directly coordinating, and the secondary sphere is having very small molecule, like there you have a H. So in that cases, this ordering, or you can say the primary crowding, is because of this oxygen, but there is no or very few secondary crowding. But what happens when your ligand structure is having some kind of moiety such as N with some kind of alkyl groups and R2, or maybe some kind of phenyl group. So beside the first one, the second one is so big that they cause some sort of steric hindrance or some sort of crowding. And because of this kind of crowding, the coordination number generally drastically get decreases. So here in this example, as you can see, the coordination number has decreased to 3. So such a decrease is mainly coming because of the secondary crowding. I have also shown you one example where the coordination number is again increased to 10. So saying the coordination number of almost 9 is okay for the solution chemistry, but when we talk about the overall compounds or the other compound of the solid state also, then the coordination number varies to a very large extent. For example, let us talk about the thorium. Thorium can have coordination number from 4 to as high as 15. So such a huge number of coordination number is possible in the case of thorium compared to the other metal ions. So in general, their trivalents are generally 9 coordinated. Tetravalents are generally, you can say, 10 to 12 coordinated. What about the pentavalent and hexavalent? Here I have shown you some example of the pentavalent. As you can see, this is having a structure that we say that a linear structure, that is this kind of molecule. And you can see these positions are called axial position, and there we say this is called equatorial position. So here you can easily see that the axial positions are already occupied, and they are occupied by the oxygen. So now the ligand has only choice to come into the equatorial plane, and in general the equatorial plane have almost 5 to 6 ligand, 5 to 6 coordination number. And here this is an example of the aqua complex where you can see 5 aqua ions are coming in the equatorial plane. So the total coordination number is 5 from equatorial, which can be 6 also, maybe 5 to 6 I can say in equatorial, plus 2 you have in axial position, which is giving a total of 7 to 8 you can say. So in general, these are having 7 to 8 coordination number. Again, the same is true for the tetravalent, same is true for the pentavalents also, because these are shown for uranium. But suppose you have a case of neptunium again, which is again a linear ion with a plus charge, and here again we can have 5 to 6 water molecule in the primary coordination sphere, or you can say in the equatorial plane, giving a total coordination number of around 7 to 8. So this is all about the coordination numbers of the different oxidation state of the actinides. So with the knowledge of hydration and the coordination number, let's just try to understand what is the thermodynamics of hydration. So as we have seen that when you put any gaseous ion or an ion in the gaseous state to the aqueous system, there is stabilization, or the overall delta G is becoming more and more negative. We have also seen that when you have a ion, there is hydration sphere. One is called primary and one is called secondary hydration sphere. And we have also talked about the number of water molecule in the primary and the secondary hydration sphere. So when the molecule is in the gaseous state, you are putting into the aqueous media, what will happen there? The water molecule will try to arrange around this metal ion, and there is some interaction between the water molecule and this metal ion, and because of that interaction there is a release of energy, or you can say the process is exothermic in nature. So overall delta is becoming negative. But at the same time, when you see the entropy factor, because we know that when you talk about the delta G, there are two factors, one is delta H and one is entropy. So there are two factors which control the total delta G value. One is delta H, which I have shown that when there is interaction between the water molecules or the solvent molecule with the metal ion, there is a huge stabilization or the isothermicity in the delta H. But what about the entropy factor? Entropy is basically, as we know, it is about the randomness. So if the randomness is increasing, entropy is increasing. But if the randomness is getting decreased, the entropy will be decreased. And here you can see when the water molecules are in the bulk, they are more free or more having more entropy. But the moment these water molecules are coming in close proximity to the metal ion, they are having some sort of structure. So now the entropy of the system is getting decreased. So in a way, I can say to the total delta G that we want to derive for the hydration of these aqueous ions, the delta H is favoring, whereas the delta S is not favoring. But the amount of delta S that is there, if you see from the table, keep in mind that these values are in kilojoule for the delta H, and for delta S it is in joule. So I have written specifically in joule because that is the unit we generally prefer. So if you use the delta H values, they are of the order of 3000 to 3500, whereas if you see the delta S, it is between 300 to, you can say, 400. So when you take total value, that is the T delta S, and you subtract from delta H to get delta G, but we found that the total contribution of entropy term to this delta G value is not more than 3 to 5%. So the stabilization is mainly coming from the delta H. So it is entropically not favored, but enthalpically very favored. So I have given you some plot. Here I have plotted all these three quantities, that is delta S, delta H, and delta G. You can see the delta H is keeps on decreasing, or I can say is enthalpically more favorable because we are getting a more and more negative value as we are moving, and the delta S is also following almost the same trend. And when we take the difference according to this equation, we are getting delta G, which is again a negative. But why this kind of trend? Because when we talk about the delta H, suppose we take delta H first, as we move in this series, what will be there? There is a decrease in the size, or you can say total increase in the Z by R ratio. So when the Z by R ratio or the ionic potential is getting increased, there is more and more stronger interaction between the metal ion and water molecule. So this interaction is becoming stronger and stronger, and because of that, the energy released is more and more. So that's why we are getting more and more negative energy. Similarly, when there is more interaction, so suppose there is low interaction at this, so the only structure of water molecule is there in the primary sphere, and the secondary is not very much influenced. But the moment you are getting to a very higher potential, a very high ionic potential, there is some sort of structuring in the secondary sphere also, and because of that, you can see there is a constant decrease in the entropy term. And then again, we just take care of entropy and enthalpy to find out delta G value, and what we found that the delta G values are again very much negative in these cases, which is giving the stabilization to the ions in the aquatic media. Once you have these ion in aquatic media, they are stabilized in some form. What else can happen to them? The next thing that can happen to them is the hydrolysis. So when you have ions in the media, they can act as a surrounded by some water molecule, that is some X number of water molecules. So the next thing that can be there is the hydrolysis, because this metal ion has a tendency to attract the oxygen from the H2O, and slowly so happens that this kind of hydrolysis equilibria can establish into the aquatic media. And as I've shown you that we are having different kind of ions, that is spherical and linear. So their hydrolysis behavior is very much different from each other. And if you assume this kind of equilibria for the hydrolysis, you can always write hydrolysis equations. And in second case, suppose you are adding to some of the alkali to the media, then obviously we can write this kind of equilibria. And these two equilibria are related with each other with the ionic product of water, and you can get this. This is a very simple mathematical equation that you can always drive, and you can get information about different kind of equilibria that is there. But the most important thing that I want to discuss here is that at what point hydrolysis will occur and which are the metal ion which are more prone to the hydrolysis. In general, as we have written, that it is dependent on the oxidation state of the metal ion. And when we say oxidation state, the trend I have given is this, that it is most prominent for the tetravalent, followed by the hexavalent, trivalent, and the pentavalent. And keep in mind that when I say hexavalent, I assume a charge of 3.3 and it is 3. So you can see there is a good decrease. You start with 4 plus and then you have a charge of 3.3, then 3, and then 2.2. So it is perfectly going with the charge on the central metal ion. The second thing is the oxidation state which are having a different structure. They are called actinides. Generally I have shown you that the actinides or the pentanol which are having linear, so their hydrolysis is very very poor, again because of the charge. So if you see the value wise, if you see the thorium hydrolysis constants with respect to others, so I have given some of the values here. If you see thorium log K value for this hydrolysis reaction is around minus 2.5, whereas for uranium it is minus 5.25. These are the log K values. So if you try to write them in the form of K, this will be like 10 to the power minus 2.5 and 10 to the power minus 5.25. What I mean by that, if you just take the ratio, you can say the thorium, tendency of thorium to get hydrolyzed is almost 500 times more than that of the uranyl ion. And when you talk about again uranium to americium, it is again almost 100 times than uranium. And this is very weak. As you can say, it is going from minus 7 to minus 11. So it is almost 1000 times lower. So this hydrolysis is taking place depending on the ions. So when you have ions and they get hydrolyzed, how their hydrolysis tendency is varying with the atomic number, we can say in the series, in the lanthanide series. So here in this particular graph, I have shown you the onset of precipitation with respect to the atomic number. Here you can see as we are moving in the chain from the lanthanum to lutetium, the pH at which the hydrolysis will occur is decreasing. What does it mean? That the ionic potential, as we move, the size is decreasing, so the ionic potential is increasing. So now the ionic potential is becoming so higher that even at low pH you can get the hydrolysis. So this is for the trivalent. Basically I have shown you the trivalent. But what about tetravalent? I've shown you in the previous slide that tetravalents are almost 500 times more prone to the hydrolysis compared to the trivalents. So when you see the tetravalent and you compare the thorium with another tetravalent, that is plutonium, if you see the hydrolysis constant, these are again order of magnitude higher for the plutonium compared to the thorium. This is again you can explain because as we are moving from here to here, there is a decrease in size, and since the charge is almost same, the ionic potential is on a very high side, and then they form hydrolysis very rapidly compared to the thorium. So when we talk about this hydrolysis for the normal trivalent, they are, or maybe you can say pentavalent and hexavalent, pentavalent mainly, they are forming a kind of complex which we say the MOH and kind of complex, which is you can say mononuclear or only with one metal ion. But when we talk about the tetravalent ion, their hydrolysis is basically, we say it is a polynuclear. Why polynuclear? Because it so happens many a time that more than one metal ions are there in the hydrolysis. When you just add some alkali, they will just make some mononuclear complex or a monohydroxy complex, and the moment you add little more alkali or the pH goes little on the higher side, they come together, all the molecules come together with the basic unit this, and they try to make some amorphous hydroxy phases. So with tetravalent, this kind of phenomena is very very prone. And I must tell you that if you see an example, if you see that let us assume that this n is 1 here, and you are having some tetravalent, and if I say that number of proton released per metal ion, so what I'm trying to say that with, if you react with this, and there is one proton release, so per metal ion one proton is released. The moment this goes to 2 or beyond 2, you can say the number of proton release goes to beyond 2, the hydrolysis is so fast or so rapid that the number of units of thorium that come together is more than 100, or you can say the cluster is having more than 100 thorium atoms in this hydrolyzed product. So the basic unit of this is this. They start with this in the very freshly prepared, and when it is freshly prepared, as I've shown you this equilibrium, when they are very much freshly prepared with this equilibrium, one can easily understand that if you increase this acidity, you can get back. So when they are freshly prepared and you are trying to increase the acidity of the medium, we are able to dissolve them. But what if they are getting aged? With time, what will happen? They make this kind of structure, and if you put it even for the longer time, they will make this kind of structure. So you can see some of the hydroxy groups are now removed, and there are oxy group. Oxidation is happening. So the tendency of formation of this is very, very slow. But if it has formed, its solubility just by increasing the acid of the media is very, very poor. So this depolymerization, this phenomena is basically a polymerization. So when I say depolymerization, we are trying to get back from this to our metal ion. So this depolymerization is becoming very, very difficult when we are talking about the aging. And this depolymerization tendency is basically dependent on the percentage of oxo and hydroxo bridging. If the percentage of oxo bridging is very high, then this depolymerization is very, very difficult. Whereas if the percentage of hydroxo bridging is high, we can have still some sort of you can say depolymerization with this. So now the question arises, okay, we know something about the hydrolysis. We know the trend, like yes, the trivalent is having very high hydrolysis constant than compared to the either trivalent or divalent. But suppose somebody asks me that, can you tell me about that? What is the fraction? What is the fraction of hydrolyzed species that is formed when I am doing some reaction at a given pH? So how we can calculate this value? So for that, I have given you some scheme. You start with the assumption that yes, you are having this kind of equilibrium, which is having the certain log K value, obviously, and then the other in which I have started from monohydroxy to dihydroxy. Sorry, it is misprinted. It should be a trihydroxy to the trihydroxy, and finally to Z amount of OH groups. So when we have this kind of equilibrium, we can write the log K value. And I assume that you are familiar with these two terms, that is the K1 and beta 2, sorry. This is the stepwise constant, and this is the cumulative. When I say cumulative, what I mean that this beta 2 is nothing but K1 into K2. So these are cumulative. So with this knowledge of log beta values and log K value, how can we arrive at the fraction or the percentage of hydrolyzed species at a given pH? So what we can do, we are having this knowledge, and whatever metals ion we are adding, suppose we have added some amount, the total M, whatever we have added, now in the system at a given pH or at a given condition is present as M free plus different hydrolyzed species, starting from mono, di, tri, all sort of species are present. So your total M is always fixed, and these fractions keep on changing depending on your pH. Suppose you can write this total M in terms of this K values, beta values, and protons. So what I have done, I have taken the relation between K1, beta 2, the relation between, obviously, between this quantity that is given by K1, and then between this quantity by beta 1. And I have tried to write all those terms with respect in terms of free metal ion and the proton concentration. So if we are able to write in this manner, what we'll get, we get a linear equation, or we get a, not linear, I should say, we get an equation like this, in which the M total is nothing but free plus 1 plus K1 by H1, B2 by H square plus B3 by H cube. So we can get this equation. Just for your for simplicity, I have assumed that suppose we have a metal ion which is just forming a mono hydroxy complex. So in that kind of condition, what will happen? I assume that this is forming only monohydroxy. So for simplicity, I am just removing these other terms. So the only thing I am left with is Mn total. That is nothing but Mn free and 1 plus my first protonation constant divided by my proton concentration. And I will try to find out what is the fraction of species or the monohydroxy species that is formed under different pH conditions. The first thing I have tried to find out the fraction of hydrolyzed species at pH 10. So for that, obviously, I have to give some log K value. So here I have assumed log K1 value of minus 11.3. So with this log K1 value of minus 11.3, what will happen at pH 10? So the relation is very simple. We know that since we have assumed only monohydroxy species, this is quite simple. We have Mn total is equal to Mn free 1 plus K1 into h to the power minus 1. And since we are having a log K1 value of minus 11.3, this K will become 10 to the power minus 11.3. And pH is, we are taking as 10. So since pH is 10, so my proton concentration will be 10 to the power minus 10. And here if you see carefully, this is h to the power minus 1. So when we write this is my h. So when we write h to the power minus 1, that is minus 1, then this will be becoming 10 to the power 10. I hope it is clear. So when we are writing this equilibrium, it is becoming 10 to the power 10. So now we just put this value, and the values are for the K1, 10 to the power minus 11. For h to the power minus 1, 10 to the power 10. We just solve this. What we found that after solving, and you just try to take the ratio of these two, what we found that at this particular pH of 10, with the first hydrolysis constant of minus 11.3, the fraction of free metal ion are more than 95%. So you can say the fraction of hydrolyzed are less than 5% or in close to 5%. We can try to find out that at a given pH, if the log K values are known, what is the fraction of hydrolyzed species that are present in the solution. Let us increase the pH to pH 11.3. Now we just do again the very simple mathematics, and what we found that at this particular pH, 50% of the total metal ion are present as free. What it means that since I have assumed the formation of only monohydroxy species, my total is nothing but sum of these two, monohydroxy and free. And what I am saying is that 50% of the total, 50% of the total is acting as a free. So this is 50%. What is rest? Rest is also 50%. So what I can say that at this particular pH, both of them are almost 50-50%. And if you see carefully, this pH is nothing but close to your log K value. It is just the negative of your log K1 value. So what you can say that if you have information about this log K value, and if you know this simple calculation, you can easily tell that at what pH, what kind of species are forming and where the hydrolysis will start. So this is the very simple case I have discussed with the monohydroxy species. But obviously in real systems, we do not have this kind of species. We generally having a combination of mono, di, tri. And in those cases, you have to take care of all these equations, all these terms in the equation, and you have to solve it. And after solving this, what you will get is nothing but a plot in which the x-axis is basically your pH, and the y-axis you can plot the fraction of the ion. So you can say initially 100% is your total or maybe free, and then with the proton with the increasing pH, there is a decrease and there is some increase in the hydroxy species. So these kind of diagrams are generally known as speciation diagram, or you can say the hydrolysis diagram, where we see that how the hydrolysis of the metal ion is taking place as a function of the pH. So here I've shown you some of the diagram for the hydrolysis of europium, americium, and neptunium. Here I have also shown you one trend that how this first hydrolysis constant is changing when you are going to the series, when you are going to the lanthanide series. Here again you can see that the first hydrolysis constant keeps on increasing when you are going from the praseodymium to lutetium. Why this? Because again here the charge is assumed to be plus 3 only, and when the charge is plus 3, size is decreasing, the Z by R ratio is again increasing. So they are having more and more ionic potential, and because of this more and more ionic potential, their tendency to react with the oxide ion, with the hydroxide ion is increasing. And you can say there is some change that is basically we called is the gadolinium break kind of things, because here if the configuration is becoming F7, that is half field configuration, and because of that there is some perturbation in this curve. Otherwise you can say this is a monotonically increasing graph for the first order constant of the lanthanides, and this I've given you the log K value and the total concentration. These are the two parameters that are required to plot this kind of graph, because as I've shown you in this equation, if you see this equation here on the bottom, what we require is m total. This is the unknown parameter, and the pH at which we want to calculate the speciation. These two things are required. Other thing, K, beta 2, all these betas are known. So if we have the information of total concentration, the log K values, this is basically the cumulative ones. So if you have information of these two, you can easily plot this kind of graph. And I hope you will try this kind of graphs, and you will try to plot them for different metal ions. So here I have shown you for europium, americium, and neptunium. So here I just want to discuss the case of neptunium, because this is the one which I have shown you for minus 11.3. As I have shown you that at pH 11.3, 50% is free. When I say free, it is free neptunium 5. And 50% is complexed. And the same situation you can see here. And this pH is nothing but around 11.3, because there is some secondary hydroxide also, but very close to 11.3. So what you can say that before this pH, the free neptunium will dominate. After this pH, the hydroxide species will dominate. And here again I'm showing you for the americium, and as you can see from the values of the first hydrolysis constant, you can say that the americium is more prone to the hydrolysis compared to europium. The values are less negative, so they are more prone to the hydrolysis compared to the lanthanides. So here the trend again is the tetravalent is giving more hydrolysis than heptanide, then the trivalent, and then the lowest one we are assuming for the pentavalent. So again I've given you some example of plutonium. One thing I just want to mention that in all this graph, I have assumed that there is no solid phase formation is happening, because if your metal concentration is on the higher side and there can be precipitation or formation of solid oxide or solid hydroxide, then this diagram may not be truly valid. So with the assumption that there is no solid phase formation, all these diagrams are drawn with this assumption. Because in case of plutonium, if you do not assume this assumption that there is no solid phase formation, you will get lots of solid phases here. Again, the example of uranium was shown here. Here what I want to show you that in case of uranium, till now, whatever we have shown you, they are only mononuclear. When I say mononuclear, only one metal is involved with certain number of hydroxy ions. But when I say polynuclear, or I can say more than one metal cyanide involved, so uranium is plutonium is also following this kind of species, but uranium is also prone to form this kind of species. You can see even at a pH circumneutral pH less than 6, it is forming this kind of complexes in which more than one uranium moieties are coming together to form this kind of hydrolyzed complexes. So with this, now we have an idea that okay, we are having a metal ion, we put into the solution, and if it is going to get some kind of reaction or some kind of hydrolysis, at what pH it will happen, and you can easily plot, or you can get some idea depending on the first hydrolysis constant, that at what pH I should start my experiment, and at what pH they will just start forming the hydrolyzed species. So I can say I have information about the speciation diagram, that what species or what hydrolyzed species in particular will exist at a given pH. But as we have read in the previous, that when we talk about these actinides, they are having variable oxidation state. Plus 7 we are not talking much because they are in highly alkaline media. So this we are not talking much. So we can, for the time being, we just assume that the oxidation state from even nobelium we are not talking much. So you can say from +3 to plus 6, and when we say plus 6 again, it is in the form of linear diisocyanate. Plus or 2 plus, depending whether it is a pentavalent or hexavalent. So now we have information of their hydrolysis, what is the trend of their hydrolysis. But since they are having different oxidation state also, how these oxygen states are varying in the solution, or do we have any information about the oxygen state that can be present in water at a given condition? At a given condition, when I say, I mean that certain PE value. What is PE? That we'll try to understand that what the term PE and what I mean by the term PE. So let us assume for very simplicity that you have a pH that we all know that what pH stands about is minus log of activity of proton. So we all know that pH level is neutral, and when we are increasing the pH to the higher side, that is in the range from 7 to 14, we are having low proton density, or we are saying that the solution is becoming less and less acidic. And when we are saying that we are decreasing the pH, what we mean that, okay, the pH is going to be decreased, it means we are having high proton density. So similar to the pH scale, which we are using for getting information about the hydrolyzed species, can we have some sort of scale in which we talk about the electrons, the availability of electron or the electron activity? So you can say very similar to pH, if there exists some scale which I can say PE, which is nothing but minus log of, you can say, activity of electrons, although the free electrons do not exist in the media, but assume that you have certain sources that somehow you are having some kind of redox couple which are able to give some electron into the media. We'll talk about this in the letter, but assume that you have some electron and we can make this kind of scale that is called PE. What will happen? As the PE will increase, what will happen that the number of electron get reduced, or you can say there is less electron density. What do I mean by less electron density? That this condition is becoming oxidizing condition, and when the PE is getting decreased, what I mean that when your PE is on the lower side, I do not have given the values of the PE, that what is the range we are talking about, we will discuss it in the later part. But suppose you have certain range from X to Y and your PE is getting decreased. When your PE is getting decreased, what will happen that the abundance of electron density will increase. So here the conditions are more and more reducing. So just to, you can always compare it with the pH whenever you are a bit confused. So then you can always compare. When we are reducing the PE, we are going to the reducing condition, and when we are increasing the PE, we are going to the oxidizing condition. Okay, so if we can use this kind of variable similar to the pH, we can always get information about the redox behavior. So we'll continue for this pH and PE relationship, and we'll see that how these variables will change the redox activity as well as the hydrolysis properties of the metal ion, mainly actinide, into the solution. And thank you for listening.